thanks for the introduction. As Phil said, there are many new exoplanets discovered, but unfortunately, the last kind of big thing we were waiting when I gave this talk like 4 years ago was James Webb Space Telescope that was supposed to launch 2 years ago, but finally it launched just in December, just on Christmas Day. So it's gone to L2, to the Lagrangian point, but still it hasn't actually started observing yet. So maybe in a few years' time we'll come and give you an update on this.
So, yeah, on the big screen. Point to the big screen. I'll make sure that mouse is there. Now try it on. No,
it doesn't seem to be working.
it was working before. Wasn't
Yeah.
It's a slide.
Battery's okay.
Oh, all the best laid plans.
Try pointing it here just in case that does something. No. Is the red mouse there? How is it? Oh, that's there. Yeah.
Okay, it seems to be working now. Okay, maybe.
I think it might be just.
It may have been that the mouse wasn't over the presentation and they launched it,
Well, yeah.
like I said.
Okay.
So the ancients discovered the first 5 planets. So I will give you some kind of updates, also some observations, but also some theoretical advancements over the last 5 years or so. So starting from ancient times, the first 5 planets is the planets we could see with our eyes, or the people back then would see with their eyes. Initially, Earth was not part of this group. Everything was going around the Earth, not the Sun, remember? Then Aristarchus in the ancient times, and then much later Copernicus added the 6th planet, the Earth. And of course, we had the discovery of the planets in the outer edges of the solar system. And that was pretty much the case until 1995, where the first exoplanet around another sun-like star was discovered. If you talk about 92, that was an exoplanet around a pulsar, which is probably a much different thing than the planets we know, the planets we have in our solar system. Since then, more than 4,000. Okay, the count goes up very fast these days. And there are, I think there are maybe around 5,000 now, and maybe there are also another 5,000 candidate planets. So there are indications that there are planets, but we have to wait for more observations to confirm this discovery. When the first planets were discovered, by the way they were moving in the sky, they were doing different things than the other stars. Initially, they thought they were kind of wanderer stars, and hence the name Asteriplanitis, which means wanderer star. So now I'm going to talk a little bit about how we can discover these planets. And the most obvious method is just point your telescope at a star and just try to look next to it, whether you can find something very dim. Okay, it's a very easy method, but the problem is that the planet is very, very faint, and it's next to a very, very bright star. So it's difficult, first of all, to observe the planet, because its radiation is very low, and it's very difficult to distinguish from the star next to it. So if you look at the opticals, so this is the radiation that our eye can detect, the planets are about 1 billion times less luminous than the star. It's really, really, really faint. But you get better opportunities to observe these planets if you instead go to longer wavelengths. So thinking about trying to observe a star with thermal imaging. So thermal imaging detects radiation that has a lower temperature, and of course the star is very hot. The planet is much less hot, so it emits more of its radiation in the infrared part of the spectrum. And this is shown in this diagram here. So here is the brightness of the star, of the object, would be the sun or the planets, and this is the wavelength. So you see the sun emits most of the radiation, the maximum here is at about 0.5 microns, which is the wavelength, the optical wavelength. And you see there's a huge difference between the star and the planets. This is a logarithmic scale. So these numbers correspond to a difference of 10 between 1 and 2. And you see for the planets, you have kind of this, their emission is consists of two parts. One is this emission here, which basically is just reflected light from the sun. So it matches, the peak matches the stellar radiation. But then there is also this emission here, which is the intrinsic emission from the planets. So you see, if you go to the infrared, that's where the James Webb Space Telescope is. That's the wavelength that it uses. The difference between star and planet, it's only about 1 million times. Still, it's very difficult, and that's why we couldn't observe many planets this way. But now we're getting to the point where we can actually do it. And to get around the problem that you're too close to the star, you look for planets that are not very close to the star. You look for planets that are quite farther away. This is the system that was the first system that was discovered with this method. And the strange was that there was not just one planet around the star, there were 4 planets. And I think even now, after like 14, 15 years, it's still, this is the only multi-planetary system that we have observed directly. So here you have the star in the middle, you have a coronagraph, so it's a device that blocks the radiation from the star. And then you can see this 1, 2, 3, 4 dots that are moving around around the star. So these planets are very massive. So they emit, usually they're about 10 times bigger than Jupiter. So they emit more radiation, so they're not that faint as Jupiter. But also they orbit quite far away from the star. So Jupiter orbits at about 5 astronomical units from the sun, but these planets are about, I don't have it here, maybe they're about from, I think, from 20 to around 60 astronomical units. So they're easier to see because they're far away. The second method that was very prominent during the initial years of the discovery, so we're talking about late 90s, beginning of 2000, is the radial velocity method. So from now on, I'm going to talk about indirect methods. So we don't really actually see the planet, we just see the effect that the planet has on the star itself. So in this case, because the star exerts a force, and also the planet exerts a force on the star. That force is very tiny, but because of this force, the star moves a little. And by looking, okay, you cannot really see the star moving, but if you look at the spectra, you can see lines moving to shorter wavelengths if the star comes toward us, and a bit longer wavelengths if the star moves away from us. So you can, by doing observations of the spectra of the star, we can see how the star moves, and you construct what they call radial velocity curves. And because if the star moves in a circle or in an ellipse, you can see a sinusoidal profile. So the star comes towards us, going away from us, comes towards us, and this continues. And these were the observations from the first exoplanet discovered by this method, by these two people, Michel Mayor and Dimitris, that they got the Nobel Prize 3 years ago for the discovery. And depending on this curve, we can get information about the planet. So a high mass planet will have a bigger effect on the star. So we'll see a bigger signal here, bigger velocity for the star. So we'll see that this yellow curve. If the planet is further away, it takes more time to go around the star. Again, you see a signal with a bigger periodicity. And if the planet is in elliptic orbit, we see of a tilted sinusoidal profile. So by studying this curve, we can get information about the properties of the planet. Then going to the third method, it's a transit method. It's the method that has given us most of the exoplanets that we know today. And again, it's an indirect method, and again, it's quite simple. So if the orientation of the planetary system is such that the planet passes in front of the star, then the luminosity, the brightness of the star will drop by a very small amount. So you get this characteristic U-shaped curve. So this is the brightness of the star versus time. And again, by the details of this curve, we can get information about the planet. So the bigger the planet, the bigger will be the drop in the brightness of the star. So it's like the eclipse we have here, the bigger is the moon. Okay, you cannot really change the size of the moon, but because the moon is big, you get a very huge drop in the brightness of the star. So here are the discovery data from the first exoplanet. It was 2001 or 2. So this is taken from ground. You see it's quite noisy. There is quite big error bars here. And these are the same data taken from the Hubble Space Telescope. So the same observation. So you can see it's very nicely defined transit curve here. The transit it's quite easy to see the transit. So there is a small percentage in the drop in a small percentage drop in the brightness of the star. And you can do that even from the ground with not such a huge telescope. Even with kind of big binoculars, you can get, if you get accurate measurements, you can actually see the brightness of the star dropping because of the planet passing through the star. But the problem is, in order to find a planet, you need to observe many stars. You need to find the star and planetary system that has the right orientation so that the planet passes in front of the star. So if you observe a system and you're in this configuration that you look, let's say from here, you're not going to see a drop, you're not going to see a transit because the planet does not pass in front of the star. But if you're on the same plane as the planet's orbit, then you will see a transit. So in order to discover planets with this method, you need to observe a large number of stars to find those stars that have the right, that have planets with the right orientation. This is very difficult to do by hand, manually, so you need to automate the process, and this is what the first generation of this type of telescopes, Kepler Space Telescope, did about 10 years ago or so. So it observed many, many stars for long enough time, because you don't need just one observation. You need to use time just to wait for the planet to pass in front of the stars. So Kepler Space Telescope observed 150,000 stars and discovered, I think, most of the exoplanets that we know today. Maybe about 3,000, if I remember well. And observed discovered planets like this system, Kepler 16b. So these are named on the order of discovery. So this was one of the first exoplanets that we discovered with this facility. So it's a planet, okay, it's an artist's impression. It's a planet around a binary star, which people before that thought it would be very difficult to exist, because when you have a binary, there are some dynamical elements that maybe disrupt the planetary system, even if there was a planet initially there. And here, this is the galaxy, and this yellow triangle just shows us the region that Kepler observed in the galaxy. So just a tiny region of the galaxy. And now we have the successor of Kepler operating. It's called TESS, the Transit Exoplanet Survey Satellite. It's a mission that started it's been now almost 5 years. So it's a all-sky mission, so it doesn't observe a specific region of the galaxy, it just observes all over. And so far, it has discovered about 200 exoplanets confirmed. And you see there are about 5,000 candidate planets waiting to be confirmed. It is expected that this facility alone will discover about 20,000 exoplanets. So going from the 4,000 that we knew before test to about 25,000 in a few years' time. So it's a really huge acceleration in the discoveries. Finally, going to the microlensing method. I think the previous method still is, this is an indirect method. And although the previous methods were kind of very simple, okay, I think it's fair to say, but this is quite kind of sophisticated method. So it uses general relativity to find new exoplanets. And the basic idea is this here that you have in this cartoon. If you have a star and nothing is between the star and the observer here on Earth, then the array is going in all different directions. So only this ray here will reach the observer. But if you have a star, another star in front of the background star and your eye, then these light rays will be bent because of the gravitational effect from this star here. So this star here acts like a lens, collecting light from the background star. So in this case, because you have more light reaching the observer, you see the star increasing in magnitude. And then when this lens moves away from the line of sight, then the star goes back to its previous brightness. And if the star here has a planet around it, then you see a characteristic blip in the brightness, in the increase of the brightness. So without a planet, the background star increases in brightness and then drops again. With the planet, you have this little thing here. And by fitting mathematical models using general theory of relativity, you can go get information about the mass of the planet and how far away it orbits from the star just by fitting this little blip over there. And this is the first planet discovery with this method. Actually, there were two blips here. You can see here in the telescope how it happens. Okay, this is a very powerful method because it can discover planets everywhere in the galaxy that they don't have to be relatively close. But the problem is it's a one-time event. You need the star to pass in front of another star exactly. So this happens, and it will never happen again. So you cannot really go back and check these observations, confirm that the planet, study the planet more. And that's the kind of the negative, the drawback of this method.
Do those blips require the orientation as well? Like transit 4.
No, you got it. Basically, they have to appear a bit different. So it doesn't matter if it's on the one side or top or at the bottom. Basically, in this case, because you have both the star and the planet also acts like a mini lens there. So about 4,500. So let's put them in this graph where I have the distance from the star here and the planet mass. So this is the terrestrial planets of our solar system. These are the gas giants and the icy giants here. And these are the observed exoplanets. You see they're all over the place and they're nothing like our solar system. You have this category of exoplanets that are called hot Jupiters. They're big as Jupiter, but much closer to the star than Jupiter. You see Mercury is here, so these planets orbit much closer to the star than Mercury orbits the sun. Okay, then you have these planets that are called super Earths, a few times, 10 times the mass of the Earth. Sometimes they're also called mini Neptunes. We don't really know whether they are more like rocky planets or more like ice planets like Neptune and Uranus. You also have the few Earths down here, Earth-like planets, and you have these very massive wide orbit planets. See, distance is about 1,000 astronomical units far away from the sun. So this graph tells us something. I mean, there's some things in this graph are real. For example, there is a gap between this group of planets and this group of planets. These are called eccentric giants. If there were more planets here, our discovery methods are good enough to find them. So there's no problem of not finding them because our method is not good enough. But down here, there may be many more planets, but they're more difficult to observe. So the effect of an Earth passing in front of the star is very minimal compared to a much bigger planet. So you should expect to have many more Earths here and maybe many more planets out there. That's just the methods are not sensitive to these planets. And there are many surprises from these planets. The hot Jupiter was the first exoplanet, was hot Jupiter. And that was basically, that's what gave the Nobel Prize to the Swiss team. So the Swiss team had the same data with an American team, but the American team was trying to find a periodic signal with period of 5 years. So they didn't look for a period of a few days that the Swiss team did. So the Swiss team announced the result, and then the Americans checked out the data. Oh yeah, we had it here. Bad luck. And of course, as I said, like the planets around binary stars. Of planets that was totally unexpected, the so-called free-floating planets. So these are observed in nearby clusters, very young clusters. This is the Sigma Orioni cluster. Okay. You see a lot of stars here, but you also see this nebulosity, and that's because there's a lot of gas still around from the cloud that actually formed all the stars. As time passes, this cloud here will dissipate. This gas will basically be lost. And when you see this nebulosity in a star region, tells you that this region is very, very young. And when an object is young, it emits more radiation than when it's older. So when you form it, the object still contracts. So basically, from gravitational, some of the gravitational energy is transformed into heat and irradiated away. So it's easier to see a small object if it's young because it's hotter. Basically, it's like boiling an egg. You boil the egg when it's freshly made, it's hot. But when time passes, it just cools down, and you know, if your observation method is your hand, you cannot really feel something that something is there.
We want the lights back on, or we're right? Hang on. You're not moving around enough.
So in this cluster, they were observed about 20 or 30, not just in this cluster, but in other regions too, planets that they don't orbit the star, they just move around in the cluster just like normal stars. And we believe that these planets were formed around a star initially, and then there were interactions, dynamical interactions with the other planets, and some of them were thrown away to become these free-floating planets. Do you remember what time I started? I don't want to talk for a couple of hours.
So you can talk for, we've got the room for another hour and a bit.
All right. Just to time.
I don't think you want to talk for another hour.
And a very interesting class of planets is planets that are what we call the habitable zone around the star. So that's the zone, basically the distance or the range of distances around a star, where the temperature of the planets is liquid water can exist. So if you go too close to the star, it's going to be too hot, water will evaporate. If you go too far away, it's going to be too cold, water will freeze. So here, this graph shows the habitable zone as a function of the mass of the star, how big basically the star is. So if you go to our sun, The habitable zone is where Earth is at 1 astronomical unit. Venus is just outside the inner edge of the habitable zone. It's too hot. Mars is just outside the outer edge. It's too cold. For smaller stars, temperature is lower, so you have to be closer to them in order for liquid water to exist. For a brighter star, you need to be further away. Quite a few planets, when I say few, maybe a few tens, have been discovered in the star. And this is the most famous one, the TRAPPIST-1 system. This star is very low mass, has just about 10% the mass of the Sun. And around the star, other planets have been discovered by the transit method. So you can see here the different transit curves. And 3 out of the 7 planets, they're very similar to the Earth and they lie within the habitable zone of the star. And you can see because the star is very small, they have to be very close to the star to be in the habitable zone. So you see their period here is about 6 to 12 days. It takes just 12 days to go around their star once. And because these planets are very close to each other, somewhere there is the distance. So you see 0.2837 AU, 0.045 AU. So very, very close together. It's easy if life develops in one of these planets to move to another planet. Imagine the kind of, if you gave the talk about what you can see in the night sky, it's going to be really big things on the night sky. And also the star will be quite big if you are so close to it. Okay, here I have like a comparison of this TRAPPIST-1 system with the Sun and the planets. Okay, this is logarithmic scale, so the sizes are kind of relative sizes are correct, but not the distances. And you see this star, this TRAPPIST-1 star is very similar to Jupiter in size, and its planetary system is very similar to the satellite system of Jupiter. You know, a very interesting system with the habitable exoplanet is the star that is closest to us, Proxima Centauri. So the stellar system that's closer to us is the Alpha Centauri system, which is a triple. So you have 2 stars that are similar masses to the Sun. They orbit very close together. And then there is a 3rd star which has 10% the mass of the Sun, which orbits about 400 astronomical units away from these 2. And around this Proxima Centauri, 2 planets have been discovered, Proxima B and Proxima C. And Proxima B is very similar to the Earth in size and is within the habitable zone of the star. But when you talk about habitable zone, it's not just the temperature. So you have to be a bit careful. It doesn't really mean that there is life here. The problem with these small stars is that for some reason they're very magnetically active. So there's a lot of X-ray radiation emitting from the stars. So it's very difficult to have planets with life around them because this X-ray radiation can destroy the building blocks of life. Basically, too energetic radiation. So let's see now how planets form. And the idea we have is that planets form very quickly after the star. So more or less they form together. And this is a very famous star-forming region, the Orion Nebula. Okay, this is the constellation of Orion. The Orion Nebula is somewhere here. And this is what you see in the optical. Okay, of course, without lines. And then if you go in the infrared, if you take a thermal imaging in the same region, you see much more structure than what you see here. So when you observe in the infrared, you see things that are called So this thing here has temperature about 10K to 20K, so very, very low temperature. And it's bright because it's relatively dense. And these are called prestellar cores. So these are kind of clouds of gas that will collapse to form the star. So this is a general cartoon of how stars and planets form. You have a gas cloud, it's quite big. Then this cloud collapses because it's too heavy. So you think in a very heavy balloon, it contracts and becomes smaller and smaller. And then when the density becomes very big at the center, then the star forms there. So even at the initial stages, there is a star there, but because there's a lot of gas around the star, it's very difficult to see. And because there is some initial rotation of this initial cloud, as it collapses, basically as its size becomes smaller, it rotates faster and faster. And so you've seen the famous experiment, maybe done at school. You have like, if you rotate around, you have your hands away, you rotate slowly, but if you put your hands closer to you, you start rotating faster, like the ice skater in an ice rink. And that's what happens here. This thing rotates faster and faster, and you form a disk, what's called a protostellar disk, around these very young stars. And in this disk is where planets eventually form. And eventually, after you form the planets, basically the disk disappears, and you're left just with the star and the planets around. And the whole process, from the collapse of the cloud to the formation of the star, is just 10 million years, which is a very short period, very short time in astrophysical terms. And this is one of the simulations that we have done at Preston that show this process. Okay. So here you see the center of the cloud. So the star has formed, and you see more gas flows toward the star, and you see the disk forming around the star, rotating like that. And you can see the disk breaks and forms. Actually, in this case, they're not planets, they're another stars. There's a binary star. This out here is a planet. And you can see a lot of dynamical interactions happening. And more gas basically falls into the central region. As I said, when these stars are very young, they're surrounded by a thick envelope of gas. So it's very difficult to observe them, but thankfully in the last 10 years or so, you have this very good interferometer. It consists of 66 antennas. It observes on radio wavelengths. And because this is very long wavelength observation, radiation, you can basically penetrate very deep inside these clouds to see the star as it forms. And because you have all these antennas, basically all next to each other, they operate like a really huge telescope by combining the signal from all the antennas looking at the same direction. And then that, by having like a very big telescope, it gives us very good resolution, which means that we can distinguish things that are very close to each other. And this facility has given very nice images of these protostellar disks that are the cradles of planets, where the planets form. So this is the first image that came from that telescope. It's called HL Tau disk. So you see this kind of dark lanes here and these bright rings that we were not able to see before without such good resolution. Basically, before this appeared like a very solid disk, no structure at all. And the idea is that planets probably form in these very dark lanes, and as the planet goes around here, it just clears up this region from the dust there. That's why they appear dark. So that was in 2015, and since then we had many more of these images from different disks. It seems that these rings here, these dark rings and bright rings are very common. The most common structure that is observed, so different instances. But you also have this with spiral arms. And these spiral arms are indications of, they're indicative of very massive disk. And you also have these crescents, which may be caused by planets being embedded, very young planets being embedded in this disk. So now let's see how we think these planets form from theoretical point of view. So initially, okay, let's see the cartoon here. You have the star and you have the disk around the star. Okay, and the disk is what you call flared. So as you go away from the star, it becomes thicker and thicker. So the dark color in this cartoon corresponds to dust, like the sun we have at the beaches, and the light color corresponds to dust. So initially, gas and dust are very well mixed. So it's like being in this room and have all the kids running around. Dust goes all over the place, right? But then when things kind of relax a little bit, the dust falls onto the floor. And the floor in this case is the disk midplane. Basically, that's where gravity pushes the dust. And as you have more dust on the floor, on the disk floor, then dust particles collide with each other and coagulate. So they join together to form something bigger and bigger. So you go from dust to pebbles, then to planetesimals, kilometer-sized objects, and finally to planets. And the picture I like to demonstrate this process is what happens under your bed. So just dust comes together to form bigger and bigger things. All right, so this is what happens under your bed, and this is what happens in space. So you see similar structure. So this is a dust grain that was brought from space, from the space in one of NASA's missions. And a way to study how this process works is in the lab. Okay, you have dust particles, and you just measure the time it takes. You throw them at different velocities to see how fast they will grow. But you can also do it in the computer. Sorry, yeah, the computer. So you put all the physics there of interaction between dust particles. It doesn't seem to be playing. This one doesn't. Anyway, let's skip that. So what happens is, this shows if you start with low velocities, collision velocities, things come together, just basically touching and being very loosely bound. If you increase the velocity further, these things kind of collide and then kind of squeeze each other, so they form something strong that can continue to grow. But if you have too high velocity, these things come together and just destroy each other. So depending on what type of velocities you have and what type of composition. So if you have icy dust, it's much easier to stick together and grow. So basically the conditions for interaction and the composition of the dust tells you how fast this process might work. And you can also do it once things started getting more bigger. So in this simulation here, it shows planetesimals, so kilometer-sized objects colliding with each other. Okay, you don't see the collision, but you see things becoming bigger here. It means that big things have collided and they have grown in size. Okay, so you see initially you have a lot of planetesimals, so a lot of kilometer-sized objects that collide with each other. And due to these collisions, the number drops, but their mass increases. Okay, so this is the distance from the star, and this is the eccentricity of these planetesimals. You can see about 80 million years here. So you started with a lot of things, and you ended up, okay, this simulation had Jupiter here, 5.2 astronomical units, and then you have the Earth, Venus, Mars, and a few leftovers, which is the asteroid belt.
Sorry, is that just purely a simulation? Jupiter popped into it.
Yeah, the simulation starts with Jupiter and a disk, and just see what happens.
Oh, it's true. Right.
So one way to grow this planet is by planetesimal collisions. We have these big kilometer-sized objects collide with each other and become even bigger. And the second way is what's called bipedal accretion. So in the case of planetesimals colliding, just only the gravity is important, right? These things are too big for gas to slow them down. So the only reason they collide, basically they close to each other, then there is the gravitational attraction. So as one thing passes next to me, just because of our gravity come together. With the pebble accretion, you have pebbles accreting on these planetesimals. And the difference in the process there is that pebbles feel gravity, okay? They're attracted by the other body, but because they're not too big, they also feel the aerodynamic drag from the gas that's still around. So it's not just purely gravitational, it's also basically acceleration due to the air that's around. And that makes it very efficient. So you can grow much faster with this process, the planetesimal accretion rather than the pebble accretion rather than the planetesimal collisions. And this is a theory that has been developed in the last 10 years or so to try to explain these very wide orbiting planets. They're very massive, these planets, so it's very difficult to form them by colliding planetesimals. It takes way too much time to do it. Whereas with pebbles, so you have smaller things accreting, but it happens all the time more efficiently. So that can give you a faster growth of your planet. I mentioned before the hot Jupiters, so very big planets orbiting close to the star. The problem of them forming there is that it's too hot for dust particles to have ices. So in our solar system, okay, Jupiter is at 5 astronomical units. It's too cold there. So dust particles have ice, so they can stick together faster and build this big planet. But if you go so close to the star, there's not enough, even dust sublimates, so the dust melts. You cannot really form this planet there. So our idea for this type of planet is that they formed away from the star and then slowly migrated inwards, moved closer to the star. Again, this is something that we study at UCLan. So here we start from a planet that we put at about 50 astronomical units away from the star. And then this planet interacts with the disk. So you see these wakes forming, these kind of spiral arms here. And because of this interaction, the planets move closer to the star slowly. And as it does so, it increases in gas by accreting material from the disk, and also it opens up this gap that you see here. Now to the very exciting stage, but because with ALMA, the telescope in Chile, and also other telescopes with specialized equipment, you can actually observe this process happening in disks. Skip that. So this is the system PDS 70. Was first observed in 2018, but there have been some successive observations that give us more information about the system. So what we have here, the star is in the middle here. Again, we have a coronagraph to probe the radiation from the star and see what's happening around. So we have this kind of, I think it's a very young planet, a protoplanet. It's about 20 astronomical units away from the star and has mass 10 times the mass of Jupiter. Okay, and if you're a bit imaginative, you can see basically this is the gap that I was just showing in the simulation before. And this is kind of the spiral arms that connect the planet with this. And with further observations, a second planet was discovered in this region up here. Again, relatively massive planet. Okay, so this is image here combines observations from sphere, from BLT, so that's a very large telescope. So that's in the near infrared, and then you have ALMA operating at radio wavelengths to construct this image. So basically now we're at the stage you can see planets while they're still forming in this very young disks. And there were more updates about the system just a few months ago. They were able to observe in detail the second exoplanet there. And if you zoom in, you can see this kind of gas around it. Basically, it's what you call a circumplanetary disk. It's like the disk we have around the stars. We also have disks around planets. And this disk that we expect is the moons of the planets to form. Like Jupiter, we have a lot of moons. We think Jupiter had a kind of a disk around it initially that gave us this moon. So very exciting times, and more observations are going to come up. Basically, this will be a routine observation to do with JWST in a few months' time, actually maybe in a year's time. So I'm not sure what is in the list to observe first. That's the priority list. So let's go now back to our solar system and just see what are our ideas about how the solar system formed and what processes were important during the early stages of evolution. Okay, of course, we have the planets in the solar system, that we know, but we have many more things. First of all, we have the asteroid belt. So many planetesimals, kind of kilometer-sized objects that are within the orbit of Mars and Jupiter here. Then if you zoom a bit out, on the outer edges of the Kuiper belt, of the solar system, we have the Kuiper belt, and Pluto is part of the Kuiper belt. So it's again a zone similar to the asteroid belt. Many objects that have kilometer size, actually much bigger than kilometer size, similar to Pluto, many objects like Pluto being there. Then if you zoom further out, we have these very eccentric trans-Neptunian objects like Sedna. So you see here is, maybe you can barely see it, is the orbit of Neptune. And then you see the orbit of Sedna, relatively large object that goes to the very far away from what we think the solar system was initially. And again, if you zoom out, going a scale of 10,000 astronomical units, so going from about 50 astronomical units here to 10,000, we have the Oort cloud. And that's the remnant of the initial cloud that collapsed and formed the solar system. I talked about Sedna. So this is Sedna. So this is the orbit of Neptune somewhere here. This is Sedna, the first of these trans-Neptunian objects discovered. And since this discovery, I think it was 2003 or so, many more objects like Sedna have been discovered. You see with the discovery, year in their name, And the very interesting and strange thing is that all of these objects have orbits on this side of the sky. And that led theorists to hypothesize that maybe there is a big thing on the other side, so-called planet line, that is needed more or less to balance this system there. So people have been trying to find this planet for the last 5-6 years, but still, I mean, you should be able to find it in the telescopes. It's with big telescopes. So it's failed, but still able to be discovered. But the problem is you need to know where to look. So if you have a very big telescope, your field of view is very narrow. So you have to check this kind of this place in the sky, then you have to move to the next, to the next, to the next. So it's not an easy thing to do. And there are models to just try to pinpoint where exactly this planet is, but again, these are theoretical models. So they may be kind of right, but they don't give you the accuracy that you want to point the telescope and find this planet if they exist. So I said, I think a few years ago, I gave an interview at a newspaper, and I said, okay, if it exists, it will be found in the next couple of years. So if you believe me, so it doesn't exist, if that's right. But we'll see. I mean, people are still looking for it, and it's a very kind of big theme. Or when you go to conferences, people are still very excited about it. So let's see what will happen in the next few years. So
why did they come with just one planet? Why not planet 9, 10, 11, and 12?
I think there were more. I think there were. You would have seen one of them.
Okay.
If you go here, here you don't see just one. You see many of them.
Yep.
So if you start seeing things on the other side, small things, then you will tell you, yeah, maybe there are more on this side, but you don't see anything there.
Okay.
The more there are,
Easier to find.
it's more, yeah, have more probability to find it. So the nice movie with kind of planetesimals collide to produce Earth, to produce Mars, it can also produce Venus. The problem with this type of simulations is that the mass that you get from Mars is quite large. This is the results of various simulations, like the one I showed you before. So it's the mass of the planet that is formed in the simulation versus its major axis. You can see it, and the squares here corresponds to the planets of our solar system. So this is Earth, Venus, Mercury, and Mars. Okay, so you can produce, and the other are data from simulations. There are many simulations. You can form something like the Earth. You can form something like Venus. But when you go to Mars, you either form something that's very eccentric. So these are the Mars corresponds here. If the orbit is very eccentric, so you're going to go close to the star, farther away from the star, or you form something that's too massive. And that's called the small Mars probe. And this simulation started with a disk full of planetesimals, and then they let these planetesimals collide to see what happens. And to solve this problem, a group of theorists proposed what's called the grand tap model. So they need to find a way to destroy the disk of planetesimals so that Mars doesn't have enough things around him to grow in mass in the models. So what they hypothesize is that initially you start with Jupiter and Saturn, and disk of planetesimals, noted by this red bar here, and another type of planetesimals with this blue bar. So these are silicate planetesimals, they're very close to the star, and this is carbon planetesimals. But that's not important actually for the moment. So the problem with these previous models is that if you have it like that, and you start forming Mars here, it will get all the planetesimals that exist in its orbit and become too massive. So the idea was proposed is that Jupiter starts migrating inwards because it interacts with the gas in the disk. So it basically destroys this disk here where Mars was supposed to be. And then Saturn also follows Jupiter and also migrates inwards. And because Saturn is smaller, it interacts better, basically, it fills the disk more than Jupiter, which is bigger. So it catches up with Jupiter as Jupiter moves inwards. And then there is a resonance and moves these two planets outwards. So things move in first, destroy the disk so they don't have too much mass for Mars to obtain, and then they move out. And by doing that, what happens is left behind an asteroid belt instead of a disk that we have here. So a lot of eccentric orbits, not as many as before. And you have a kind of a dual composition for the asteroid belt, which is something actually observed. So it was another success of this one.
Excuse me, when you run a simulation, you have a fixed set of variables that you input. Do you get the same result every time you run the simulation?
For exactly the same variables, you should get the same result.
You should, or you do? You do?
Yeah, you do. If you don't do, then it's wrong, so you have to fix it. But if you change a little bit the initial condition, you get something different.
Which is what you're doing to try and come up with.
So what you do is you do many different conditions,
yeah,
and just try to see in a statistical sense whether you will get the result that you want. So you don't just do one simulation and trust it. You have to do many.
Couldn't that explain why Planet 9 doesn't exist? Because the circumstances that form the other planets are in a set of variables that didn't produce Planet 9.
I don't know, but because the hypothesis of Planet 9 is just basically on dynamical considerations. So because you have all these things on one side, and then what happens?
When
You have so you have a lot of things to constrain what's on the other side, not just assuming. So you don't try to understand how this thing evolved. You just have this, and then you say, okay, I want to make this statement. What do I need? So I think that's a bit easier than this one. So for that one, you see something and you say, okay, is there something that I'm missing here that shouldn't be there for the system to be complete? Whereas here, okay, you have the final thing, and you say, okay, how could I get from something totally different to this final? So it's I think it's a bit, I think this one is a bit more difficult. And I will show you now the movie. So what you have here, I think if I remember well, this is Jupiter here, the orbit of Jupiter, and this is the orbit of Saturn. And you have a lot of planetesimals, so the red planetesimals and the blue planetesimals that have different composition. Okay, things happen fast now, so I think we'll have to play it a couple of times. Okay, so you see Jupiter moving inwards. Then Saturn moves inwards quite fast, catches up with Jupiter, and then both of them move outwards. And it's called the Grand Tack model. I'm not sure how many of you are aware of the term. Kind of in sailing, basically, when you're going to go against the wind, you cannot really go against the wind, right? So you go in a zigzag against the wind. Okay, Jupiter moving inwards. Saturn starts moving fast inwards, catching up with Jupiter, and then there is a resonance and both of them move outwards.
Sorry, why do they move outwards? Is that just mass?
Sorry?
Why do they move outwards then? Is that just mass that changes? Because the mass is changing.
No, the mass remains the same. Just actually, I don't understand why they move out. It's just a resonance.
Right.
And basically, they behave like one object, and somehow they go against the wind.
Oh, okay, right.
So whether you migrate, usually the migration is inward, but it's a very fine balance between interactions with the planetesimals inside and interaction with the planetesimal outside. Okay. So depending which type of interaction is more prominent.
Right, right.
So if you interact more with the particles, with the planetesimals that are outside, then you give energy to these planetesimals and move inwards. And the other way happens with if you interact with the things that are inside.
Okay, right.
So that's, we think, what happened at the beginning of the solar system when there was enough gas. But there's also some evidence that things happen, kind of a lot of dynamic interactions happen relatively late during the formation of the solar system. This is called the late heavy bombardment period. So when you do some radioactive dating of lunar rock samples, there were many craters about 700 million years after the formation of the solar system. And we think that this is due to another instability that happened involving planetesimals much later than what I showed now. And this is called it's not the nice model, it's a nice model, but it's called the NIS model from the city that was developed. So what in this model, okay, it starts, what I have here is the distance from the star versus time. So this model starts with Jupiter, Saturn, more or less at where they are today, and then Neptune and Uranus, so basically opposite to what they are today. And also they put a Kuiper belt in this system. So a lot of planetesimals, kilometer-sized objects outside the orbit of Uranus. Again, because of these interactions with these planetesimals that are quite far out, Saturn and Jupiter, okay, initially they move more or less independently, but then they go to a resonant motion again, more or less the same thing happening as before. And when you do that, being in a resonance, okay, maybe I need to explain that. So if things the two resonance, right, which means that if Jupiter moves around the sun once, Saturn moves at the same time move around the sun twice. So every time they're in this position, Jupiter gives a little kick to Saturn. And it's the same kick happening every period. And then basically it's like the swing, right? If you just pushing someone kind of randomly, it won't happen anything. But if you push him at the right point, you don't waste much energy and the oscillation becomes bigger and bigger. And that's what happens here. When there is this kind of magic number 1 to 2, they interact very strongly and they become eccentric. So you have a stable system, and then these things become eccentric, and then they affect the planets outside them. So the system is more or less stable than before. You see they evolve in a straight line. The distance from the star doesn't change. But then something happens when this resonance happens, and they just get crazy a little bit, and they go to a new configuration. Okay. I'm also going to have another move here, which again happens very fast. So everything is stable. So these are the Kuiper belt, the planetesimals outside the opposite of Uranus. Looks kind of nice. You see, 500 years, million years, nothing happens. And then Jupiter and Saturn come in resonance. And just happening. And you see there's a little left of the planetesimals. And that's what we see today. They don't have a huge mass in the planet, in the Kuiper belt. One more time. See, things are getting a bit wiggly here, so there is some kind of interaction. But then this thing built up slowly. And then it scares. You see kind of the flip of the orbits of Neptune and Uranus. And again, what they did is not just one model, they did many models to just find what is the most likely outcome from these models. And actually, there's the configuration of the system that we have today is not a very common outcome from this from the simulation. But it is a possible outcome. Okay, and this is basically summarizing these two together. It's what we think about our solar system. So I think these ideas have been developed in the last 10, maybe 15 years maximum. So we have, so this evolution with time, and this is the distance from the star. Okay, so initially you start with a planetesimal disk, so the color here corresponds to kilometer-sized objects, and the planets being Jupiter being more or less where it is today. And then Jupiter moves inwards, so that the grand tack period, 0.2 million years. Then with Saturn, they move together out, and that's 0.6 million years. The system is more or less stable, going to 800 million years, and then Jupiter and Saturn become in resonance, and then the Neptune and Saturn and Neptune move outwards. Sorry, I was
Uranus.
yeah, that's Uranus. I was confused by the rings there.
That's all within the first billion years of the solar system.
Yes, and then basically nothing happens.
We live in a boring time.
Yes. Well, I think we're lucky the first time, right? We don't want many asteroids coming towards us. Okay, so you start something that is kind of a planetesimal disk that's very well defined in composition. So red, light blue, and dark blue, and then you have things that are mixed here, things that are mixed here. And coming now to our time. So that's the James Webb Space Telescope. I think it's been in the making for quite a few decades, actually. So finally launched in Christmas a couple of months ago. Everything went all right. It took about a month, but it reached the Lagrangian point. Just to compare it here with Hubble, it has much bigger mirror. I think Hubble was 1.2 meters or 1.6. I think 1.6 meters. This is 6.6 meters diameter, so much more collecting area. So that means you can see things that are fainter. You can distinguish between things that are very close together. It operates in the near infrared, so at longer wavelengths than the Hubble Space Telescope. So you can see this is the region where planets, exoplanets, will emit more radiation. So it's a good thing. It's quite big compared to a tennis. This is compared to a tennis court. It was quite a mechanical feat. Basically, it didn't go up. I'm not sure if you watched the news, but it go kind of went upstairs, got tightly packed, and then it assembled itself, kind of expanded like a flower, and did all the mirrors and everything once it was up there. And in contrast with Hubble, it will not orbit the Earth. So Hubble was around there. So the good thing was that it could send people to fix it if something was wrong. And many things went wrong over the last 30 years. So the James Webb Telescope, it's at L2. So it's a kind of a point of equilibrium of the system, the sun, the Earth system, the sun-Earth system. So when you have two bodies, you have 5 points that you have the minimum 5 points that are stable points. So if you put something there, you don't waste much energy to keep it there, just stay there more or less by itself. So that's quite far away, you see. So you cannot really send someone there, although maybe it's a good. If you have nothing to do, maybe it's a good thing to try for the future. But yeah, it took like about I think it took about a month to go there, and in about 6 months we're going to have some. I think it collected the first photons, not real observation, just to test some systems. but yeah, in about 6 months, we're going to start getting the first observations from this very important mission. And apart from that mission, there are other many missions that are dedicated to exoplanets. We go up there to try to observe exoplanet atmospheres to see what the atmosphere is made of and whether actually you can have life on those planets. And the way to do it is with a method called transmission spectroscopy. So, okay, most of these exoplanets are too far away to see them, even with James Webb's telescope, to observe them directly. Some of the closest one, you will be able to see them directly, get an image and see what is the composition of the atmosphere. But for most of them, we will do this one. So if you have this configuration, you have some lights from the star passing through the atmosphere of the planet and reach your, okay, this is the Hubble, but you can put the James Webb's telescope there. So when you see this light from the star, it's going to have these absorption lines depending on what you have in the atmosphere of the planet. Okay, and then from these lines here in the spectrum, you can get information about the planet. Okay, so you can actually see there's oxygen, there's this big kind of absorption lines. Here you can see there's water, characteristic wavelength for the water, CO2, and all the other elements that you expect to have in the atmosphere. Okay, so exciting times. I think maybe I can come in 5 years' time to give just the talk about the JWST. I'm very looking forward to see the observations from this telescope coming up.
It'll be 50,000 exoplanets. 500,000.
Yeah, initially we kind of have the few exoplanets that were making nice clothes and everybody was happy, but now it's just getting a bit crazy. You can't just put like 10,000 points in one graph. You don't get much. Okay, so yeah, you can see basically what type of atmosphere you have from this spectra, and of course, what you're trying to find is something like that. We'll see what you can get. So thanks a lot.
Thank you.